following problem is similar to the demonstration we did in class with the accelerating fan cart and the constant velocity army cart. In this problem, the two carts are on a collision course. The fan cart accelerates at 0.18 meters per second squared, while the army car runs at a constant velocity of 0.4 meters per second. If the fan cart starts from rest at a position of 5 meters and the army car starts at the 1 meter mark, where will they meet? Like every problem, let's draw a sketch to make sure we understand what's going on. And so I'm going to draw a picture of these cars. Now we're given a couple positions, and this is a one-dimensional problem. It appears the army car is at the 1 meter mark with the fan car at the 5 meter mark. So as I interpret it, I'm going to put my army car here at the 1 meter mark. Call that 1 meter. And over here is my fan cart. And it's at the 5 meter mark. The army car has an initial velocity of 0.4 meters per second. And the fan cart is going to accelerate towards the army car. They're on a collision course, so they're heading towards each other. And we know that we have an acceleration of 0.18 meters per second squared to the left. Now it starts at rest, so it has no initial velocity. And they're going to meet somewhere in the middle, which we actually don't know. We'll call that x final. So anytime you have multiple objects moving and they're interacting with each other, every object that is moving should get an ATVX table. Basically, their motion can be described by those variables, and we can write some equations to relate them. So let's start with our army car. And the army car is going to have an acceleration, a time, a v initial, a v final, an x initial, x final. And the fan cart is going to have those variables as well. Now, we want to make sure we put in the right values. So what we do know is that army car has an initial velocity of 0.4 meters per second. However, it's at constant velocity, and constant velocity means the velocity is not changing, which means it is not changing its velocity. So it has zero acceleration, which means the final velocity is also 0.4 meters per second. And this side of a problem basically is just the one constant velocity equation. For reference, I'll write down the two equations that we do use. We have x final equals 1/2 at squared plus v initial t plus x initial. That describes the position of these cars. And their velocities are described by v final is at plus v initial. Again, that's a linear function of the velocity time graph. Now, the army car will start at the 1 meter mark, and it's going to finish somewhere we don't know, and it's going to get there at some time we don't know. The fan cart is going to be moving towards the army car. Now, I didn't put it on my drawing, but it's always helpful to reference the fact that I'm calling the positive direction to the right. I've indicated that I've got a positive velocity, and therefore my acceleration, which is to the left, needs to be negative 0.18 meters per second squared. All right, this is to the left, which is where the negative sign comes into play. We don't know when they'll collide. It has zero velocity to start because it starts at rest, which is an important thing to notice in the problem. And it's going to have some velocity when it strikes the car. We don't know. It starts at 5 meters and it finishes somewhere. Now, these two cars collide, and what we do know is when they collide, their clocks will read the same thing, and their location will be the same. And so we effectively have these two variables, time and final position, that are shared between them, even though they have different tables. So now we can get to solving this problem. There's a couple ways to look at it, but we're effectively solving a system of equations. And we're trying to find their position. So we're going to use our position function, and we can model the position of each car at any point in time. So for our army car, the final position of the army car is 1/2 of 0 t squared plus its initial velocity times time plus its initial position. And the final position of the fan cart is 1/2 of negative 0.18 t squared plus its initial velocity, which is 0 times time plus its initial position. And we can clean up those equations because those zeros basically wipe out those terms. And you get a simplified equation to describe the motion of the fan cart as our constant velocity equation. And, sorry, that was for the Army car. And for our fan cart, you get negative 0.09 t squared plus 5. So you now have two functions describing the motion of each car in terms of time and position. We have a system, and now we're going to solve the system of equations. And algebraically, the easiest way to solve this would be to take what x final equals for the Army car, substitute it in for what it is for the fan car. You get a new equation, which is 0.4t plus 1 equals negative 0.09 t squared plus 5. We call this setting them equal to each other, but really it's just substitution. And then I'm going to collect the terms on one side of the equation. So by subtracting 0.4t and 1, organizing my terms, I get a new equation that is, and when I write it in standard form here with decreasing powers, negative 0.09t minus 0.4t plus 4. And that's a quadratic function. We have the quadratic formula, which hopefully you guys have programmed into your calculator. So all we need to do is identify our a, b, and c terms, which are the coefficients of the t squared, t, and the constant. And I'm going to type them right into my calculator. I have a program that is doing the math for me that I've already programmed. Negative 0.09 is the t squared term. Negative 0.4 is the t term, and positive 4 is the c term. And I get two time values, negative 9.25. T equals negative 9.25 seconds, and 4.81, positive 4.81 seconds. Now, in the real world, we don't really have negative time. That would be the time that occurred before the race ever started. So I can throw away this time. That becomes the time of the impact. But the question asks, where are they located at this time? So I'm going to take either one of those original equations. I'll take the first one. It's nice and simple. And I'm going to plug in 4.81 seconds into that equation to find the final position where they're going to collide. 4.81 times 0.4 plus 1, and I get 2.92 meters. That's where they're going to collide, which should be between 1 and 5, which in fact it is, and there's our answer. So again, this is the algebraic way to solve this system, and it basically comes from finding two functions to describe the motion of those cars. Now I want to show you a second way. So we're going to call this option 1 as a way to solve. Option 2 would be to graph it. And what we know about position functions and our position time graph, we can plot these two. If I plot the Army car, it's going to start at a position of 1, and it's going to move away from that position in the positive direction at a steady rate. It's going to have a slope of 0.4 meters per second, right? That's our velocity of a position versus time graph. The fan cart's going to start up here at 5 when time is 0. It's going to have no velocity early, and it's going to steadily increase its velocity in the negative direction. If you were to look at these slopes at any time, it's getting faster and faster in the negative direction, and so you get this shape. And what we're really looking for is this intersection, which represents a time and a final position when they meet, which is exactly what we're looking for. So if I can find what that is, I'm golden. The nice thing is the equations that we have are exactly what we just showed here. So I can go into my y equals, I can put 0.4x plus 1 for one function, and negative 0.09x squared plus 5 into the other function. And when I hit graph, we'll see there's one line, and there's my downward facing parabola that crosses at 5. And you see that in that quadrant 1, the top right, that's where time is positive and position is positive, which is what we're looking for. And so what I'm trying to find is where is this intersection? Notice there are actually two intersections, one up on the top in quadrant 1, one in quadrant 3, which was before this occurred. So when I want to find the intersection, I go second trace, which gets you to our calc area. And I want to do option 5, which is the intersect. And I'm going to click one graph, click the other graph, and then make a guess. Right now my cursor is closer to this intersection on the right, so if I hit enter, it'll jump to that spot and tell me the coordinates of that point. The coordinates are 4.81 and 2.92, which correspond, again, to our time of impact and our position, right, which is what we found in the other way. So just showing you another option, which might actually save you some time, and hopefully you recognize that there's some value to understanding how these graphs work. So hopefully this will help you as you're preparing for the test with a problem where we have an accelerating object and a constant velocity object and a system of equations to solve it. Best of luck.